Most of rotation has been an application of concepts we saw earlier in the semester in a different way. However, the law of conservation of angular momentum is something new. It is the punchline to our entire discussion of rotation. In an earlier video, we defined momentum as mass times velocity. It is a vector, and it is useful in solving collision problems. Angular momentum has an analogous definition: moment of inertia times angular velocity. Angular momentum is symbolized with the capital letter L and is measured in kilogram meters squared per second. It is a vector quantity as well. Just like angular velocity, we will use the convention that an object rotating counterclockwise has positive angular momentum, and an object rotating clockwise has a negative angular momentum. The law of conservation of angular momentum says that if you have several rotating objects, their total angular momentum before they collide must equal their total angular momentum after they collide. It also says that when the moment of inertia of an object decreases, its angular velocity must increase and vice versa. This is most famously seen in figure skaters. They decrease their moment of inertia by drawing in their arms, and as they do so, they spin faster and faster. Consider this skater. She is initially spinning at 3 radians per second counterclockwise. With her arms outstretched, she has a moment of inertia of 3 kilogram meters squared. As she draws her arms in, her overall radius decreases, and with it, her moment of inertia. If her new moment of inertia is 1.75 kilogram meters squared, what is her new angular velocity? The law of conservation of angular momentum states that initial angular momentum must equal final angular momentum. Let's expand this with the definition of angular momentum: moment of inertia multiplied by angular velocity. And then let us substitute in the known quantities. Her initial angular momentum equals her moment of inertia, 3 kilogram meters squared, times her initial angular velocity, positive 3 radians per second. Her final moment of inertia is 1.75 kilogram meters squared. So her initial angular momentum is 9 kilogram meters squared per second, and we can easily figure out that her final angular velocity must be positive 5.14 radians per second, which is counterclockwise. Here we see a carousel with a radius of 3 meters and a mass of 50 kilograms. It is standing still. A 10 kilogram dog runs around it in a circle at a speed of 2 meters per second and then jumps onto the rim. How fast does the carousel rotate? We have to compare the overall angular momentum of the dog and the carousel a nanosecond before they made contact to their angular momentum a nanosecond after the dog landed. The dog was running around the outside rim of the carousel at 2 meters a second. We can calculate its angular velocity by dividing v by r. That gives us an angular velocity of 0.66 radians per second, and since the motion was counterclockwise, we consider this as being positive. We can consider the dog to be a point orbiting around the center of rotation. Such a point has a moment of inertia of mr squared, where r is the radius of the orbit, or equivalently, the distance from the dog to the center of rotation. That works out to 90 kilogram meters squared. We can also work out the moment of inertia for the carousel. We can treat the carousel as a cylinder. Its moment of inertia is given by 1/2 mr squared. That works out to 225 kilogram meters squared. Now, let's apply all this information to conservation of angular momentum. The total momentum before the collision equals the total momentum after. we can expand out the total momentum to account for the individual momenta of the dog and the carousel, and then we can expand those to account for the definition of angular momentum. We can substitute in all we know. Originally, the carousel was standing still, so its angular velocity at the beginning is 0. When the dog jumps on, it remains at its original distance from the center, that's 3 meters, so its moment of inertia hasn't changed. The other thing is, after the dog jumps on, it spins at the same rate as the carousel, so the angular velocity of the dog after it jumps on equals the angular velocity of the carousel. We can therefore solve for the final angular velocity of the dog and the carousel. It works out to 0.19 radians per second. Suppose the dog is at the rim of the carousel. Remember, the dog is 10 kilograms and the radius is 3 meters. And the carousel is rotating at 5 radians per second. The dog then jumps off, landing at rest. What is the angular velocity of the carousel after the dog jumps off? The rotational inertia of the dog is the same as it was in the earlier puzzle, 90 kilogram meters squared. In fact, it would stay the same as long as the dog stays 3 meters from the center. Since the dog ends up at rest, its final angular velocity is 0. We can plug in all the known information, and then we can solve for the final angular velocity of the carousel. It is 7 radians per second. It's positive, which means the carousel continues rotating counterclockwise. Suppose the dog is back on the rim of the carousel and both are initially at rest. Then the dog starts running around the rim at -8 radians per second, that is, clockwise. How does the carousel respond? Again, we can plug in all the known information into conservation of angular momentum. The initial angular velocities of both the dog and the carousel are 0, and it's easy to solve for the final angular momentum of the carousel. It is 2.4 radians per second, which is counterclockwise. In this video, we discussed the law of conservation of angular momentum, and at this point, we have seen many of the principles associated with rotational motion. For our purposes, this will also be the last lesson for this course. As always, I'll be available by email or Zoom to answer any questions you have. Thank you, and above all, take care of yourselves.